All right, let's look at an example. Let's look at the example of control of production and consumption. All right, so suppose we have a factory whose output we can control. So we can um, affect as a factory work or factory management how much we actually produce in this factory. Um, so then we can construct this mathematical model by basically selecting X as the amount of output produced at time T. And now suppose that we can consume some fraction of that output at each time step, okay? And then we can take that output that we consume and then reinvest the remaining, right? So we're gonna call alpha as this fraction of output reinvested at time t. All right, so we're going to say that alpha, let me pull up my writer here, great. Okay, so this will be, alpha is going to be our control. And it's subjected to the following constraints. Namely that alpha t is greater than 0 and less than or equal to 1 for all t greater than or equal to 0. All right. So given this control, the corresponding dynamics for this type of system can be modeled using an exponential like system. Well, the solution will be exponential. All right, so it's a first order where we have k, alpha, t, and x. All right, so the solution, if k and alpha are constant, the solution to this will be an exponential function, right? If k and alpha are positive, it'll be an exponential increase. If k and alpha are negative, well, if one is negative, then it'll be an exponential decay, right? So for this system, the constant k is greater than 0, which models the growth rate. All right, and then we can take the payoff functional. Let's say the payoff is given by p alpha is equal to 0 to t, the integral of 0 to t, 1 minus alpha t x of t dt. Okay, so this means that we want to maximize our total consumption of the output, our consumption at a given time t being this guy right here. All right. And so this fits into our general framework for the states, the state space Rn is equal to just the reals, and Rm is just the reals. And so we basically, this fits into our general framework. This fits framework with m equal 1 A, which is the space of our control inputs, 0 to 1, f as f of xu equal to k ku and x. R is equal to 1 minus, oh, this will be L is equal to 1 minus A times X. Get my notation mixed up. U. And lastly, we have phi is just equal to 0. So, as we'll see later when we talk about bang-bang control, this results in the solution to this, the optimal control for this will be what's called a bang-bang controller. Alpha star is given by so 1 if t is between t and t star, and 0 otherwise for all t greater than t star. So where t star is in the interval 0 to t, is the switching time, right? So this is the time at which you go from full throttle to nothing, to no input. Okay. So what does this mean? Well, one, what does this look like? So this function is, as you can imagine, if this is t, we'll have a t star. It's a t star here, a maximum time here, and 0 here. And then in the vertical direction, we'll have 0 and 1, right? So essentially, that line will be our switching time. And then alpha will go this way. This is alpha. And it'll reach t, and then it'll jump to 0. And right, so that's what the function looks like. So in other words, basically what this is saying, this bang-bang controller, is that we should invest all of the output up until time t star, and then after this time, we should consume everything and reinvest nothing. So the switch over time, this switching time, t star, is something that we'll need to determine through the analysis that we do. And then so this is called, so this alpha, this should be alpha star. So alpha star here is called a bang-bang controller, right? Which in general just means that you're oscillating between the two maximums of the definition of your controller space. So if this is a similar form of this would basically be a saturation function, where you cannot have infinite control input into your system. You have upper and lower bounds. And so the solution will be basically going full throttle one direction, full throttle the other direction. Other way to think about it is if you're looking at a car model, also known as a Dubin's model, which has bounds in the turning radius, you can, a particular solution to this for basically resource finding is to go full turns in one direction and full turn in the other direction when you need to turn, and then just go straight. So it's called a bang bang controller. Next, I'll do one more example, and then move on into some analysis.